Good morning, everybody, and welcome to National Astronomy Week 2020. This year, due to current craziness and restrictions and COVID, we are in a virtual environment. So if you haven't been to an NAW session yet this week, this is now day 6 of 9, so welcome to you all. We have people joining us on Zoom and on YouTube and from outside the UK and within as well, so hello to you all. Now, the National Astronomy Week, it's supported by a variety of organisations, so we have them to thank. It's their job to help us promote astronomy and space education for all ages. I think so far we're up to something like 72 speakers and hosts and practical astronomers who are all giving up their time this week to help deliver these sessions. And today is an exciting one, which I've been looking forward to. Our theme is robots on Mars. So a quick introduction. My name's Alistair Bruce. I'm an astronomer by training. This year I started working at Dynamic Earth as their planetarium manager, just in time for a pandemic. So I'm currently sat in an empty dome, which is the way it usually is, but I've got you a nice view from the office, so to speak. My co-host today is Richard as well. So Richard, say hello, introduce yourself.
Good morning. Yeah, I'm not in a virtual environment. This is my home. I'm slightly off message because not only am I not in Scotland this morning, but I'm also wearing a Jupiter hoodie, I'm afraid. We're going to be talking about Mars. So I am a science journalist, which means I write about space. I write about space for the BBC Future website. I also make radio programs on space and 2 podcasts, the Supermassive podcast and the Space Boffins podcast. And I do some work for the European Space Agency. So I commentate on launches for the European Space Agency. So if you watched Tim Peake's launch to the International Space Station 5 years ago now. So it was me who was commentating on the launch, describing the rocket going into space and describing Tim arriving on the space station and his appalling choice of music as he waited for liftoff. So that's me. I'll be back later to help with the Q&A, and I encourage you to leave questions for us.
We have 4 fantastic speakers for you today. So I think we're going to go full Brady Bunch and get all of them to switch on their cameras at the same time and give us a wee wave. So we have Anya O'Brien from the University of Glasgow. We have Sarah Matagian from the Natural History Museum of London. We also have Nina Cameron and Katie McKinnon, who are the core of the Glasgow Science Centre planetarium team. So give us another wave, everybody. I feel like I should have the Brady Bunch theme tune or something, which is great. So I'm just about to hand over. So as Richard said, please do leave your Q&A questions. Myself and Richard will try and parse them as best we can, and we'll ask these questions of our speakers at the end of the session. But in the meantime, I'm going to hand straight over to Sarah and Anya. The virtual floor is all yours. So happy to have you. Thank you.
Hi everyone, my name's Anya. I'm a PhD student at the University of Glasgow. My PhD is all focused around the understanding of whether or not there's ever life or the ingredients for life on Mars. Sarah?
Hey, so my name's Sarah and I'm also a planetary science PhD student, but I'm at the Natural History Museum at Imperial College in London, and I'm working on some of the spectra instrumentation for one of the next Mars missions called ExoMars.
And we are here today to basically talk to you about some amazing activities you can do with rovers, and you're going to get a chance to do your own today with our colleagues from the Science Centre, Katie and Nina. Nina and Katie, do you want to introduce yourselves quickly now?
Hi, my name is Katie and I'm one of the presenters in the planetarium at the Glasgow Science Centre. So usually I show you around the stars and the universe, but today I'm going to be showing you how to make your very own rover.
Good morning, everyone. My name is Nina Cameron. I'm the planetarium coordinator at Glasgow Science Centre. I'm an astrophysicist by training, an astronomer by accident, and I'm lucky enough to run the largest planetarium in Scotland. Sorry, Alistair. I'm going to be talking a little bit about some of my favourite robots on Mars, just to give you a bit of inspiration for building your own rover with Katie. I'm going to stop talking, hand over to Anya and Sarah, and they're going to talk about their exciting project, Roving with Rosalind.
Thanks, Nina. And just a quick thing to say to you all watching today, thank you so much. But we did have original grand plans to all be together in the space zone, socially distanced, of course, of the space zone of the Glasgow Science Centre. But unfortunately, with Scotland, Central Belt of Scotland going into Tier 4 restrictions, it was decided this just wasn't the right thing to do. So at last minute yesterday, we had to change our plans for this session. So please bear with us if there's any hiccups. We didn't plan to have 4 of us doing it all separately. So yeah, like like everyone's lives in 2020, things might go a bit upside down. There might be toddlers and cats crawling about. So that wasn't very much in the plan, but hopefully you can bear with us and have a good time today. So first of all, why rovers on Mars? Why are we excited about that? Why is it something you should care about? Well, Mars is a really cool planet because there may well be life there or have been life in the past. Life as we know it is kind of all based around water. It relies on water. But if you look at Mars now, looks like a pretty dry, kind of inhospitable place. But certainly around about 3 billion years ago, it had loads of water. It was a really wet planet. It's also, most similar neighbour to us in our solar system compared to Earth. And because of that, we think it's got a pretty good chance of having extraterrestrial life on the red planet. So as scientists, so Sarah and I are both Martian scientists, we're dedicated to the exploration of Mars. We want to go there, we want to analyse it, but we don't want to send people there just yet. We want to send basically roving laboratories that can do everything or almost everything we can do on Earth, but on the planet itself. So Sarah is going to talk to you about an opportunity you all can have if you're in a school classroom, in a Brownies, Scouts, Guides troop, science club, anything like that, to get involved and actually do real Mars science yourself.
So we hope that you've maybe seen a little bit of our project this week. It's called Roving with Rosalind. Anya's beautiful background has our little logo on it. So Roving with Rosalind is a nationwide project that we've developed that's going to help get real Martian science into the classroom with you guys. So some point in the hopefully very near future, if COVID allows, we'll have our kits up and running, and your school, your teacher, the leader of your group can request to borrow them, and you can start doing some real mission-like science like Anya and I do in our day-to-day jobs. So the main or the biggest part is getting to explore Mars for yourself. So we're going to give you lots of different ways to explore a map of Mars, and then you're going to find some interesting samples, just like we do on mission. So Anya's just going to tell you a little bit about some of those.
Yeah, so one of the highlight, if you like, of these kits, and they're totally free to borrow, by the way. We've funded them to build them from the UK Space Agency, and we have the funding to send them out to schools and activity groups across the country. So it's totally free. And we have these adorable little Lego rovers that you can build and basically program and code and design to explore your own map of Mars. So you'll be able to design a little route to explore a giant rug, if you like, map of Mars, and you're going to be able to see, okay, how do I decide where it goes? How do I learn how to control a rover? What do I have to think about? And then you'll be able to do that with Lego ones. You also have some remote control ones that you control with iPads where you can see through the eyes of a rover, and you guys will pretend to be mission control and have a think about exactly the kind of challenges we have communicating with a robot thousands and thousands of miles away.
It's pretty tough. So it takes a whole team of people to do it. But in your little mission control groups, once you've explored your map of Mars and you find some interesting samples, the next thing you're going to get to do is you're going to get to work with data just like we do on the mission. So we got some amazing instruments on board the ex-Mars rover, Rosalind Franklin, like PanCam, ISM, and HRC. So you're going to get to work with data that looks just like that, just like we will when the mission actually lands. Discover some different things that you might have found there, and then make some conclusions about the area. So maybe you found life, maybe you found evidence of water. You'll have to borrow the kits and see.
Brilliant, amazing. So what I'm going to do is drop a link in the chat for anyone, any teachers, parents, guardians, activity leaders watching here today to drop us a line and say, hey, you want to borrow this kit, and we'll sort that out for you. So hopefully that'll be an opportunity you guys want to get involved with. But without further ado, let's focus on the main thing for today, which is things you can do at home. So what's going to happen is shortly, Katie is going to show you how you can build a rover yourself out of recycling, out of things you find around the house. But in order to do that, you kind of need to know what's in a rover, what's it made of, what's the point of these adorable little things. So Sarah has spent a long time putting together a mock-up in Lego of the ExoMars rover. So the ExoMars mission is a mission going to Mars. It's leaving in 2022 and it should be landing in 2023. It's named after Rosalind Franklin, which is why the name of our project is Roving with Rosalind. Rosalind Franklin was an X-ray crystallographer. posh word, but basically she was instrumental. It was thanks to her that we understand the structure of DNA. So almost everything we know about our genes is down to her figuring out this sort of, it's called a double helix, basically a spiral structure of our DNA. And so Sarah has built a model of the rover out of Lego, and she's going to talk you through all the different components that come together to make a rover. And then shortly after, Katie is going to talk you through how you folks can get hands-on today and build your own.
This isn't going to be an exhaustive list because it's very, very complex to design a rover, but I'm going to try and give you highlights so you can decide what your rover is going to look like. So as Anya said, this is as best an approximation of the ExoMars rover as I could do out of the Lego that's currently available. So let's just start with the kind of fundamentals. It's the shape and size of our rover, or what we're going to call the structure. So for the ExoMars rover, Rosalind Franklin, it has what is affectionately called the bathtub, which is this kind of structure at the bottom, this kind of tan color. And this is what houses all of our instruments, all of our payload, any of our sensors and things like that. So the size and shape that you make your structure will inform what instruments you can have, the mass limits, the volume limits, and things like that. So it is really tempting to just build an absolutely giant rover and put every single instrument that we can think of on it, but it's really hard to launch something that massive off the surface of Earth. So we have to, there's a little bit of a trade-off. We have to decide what the mass the maximum mass for a rover that we can have, and then use that as best as we can to do the science that we want on the surface. So the next thing we're going to talk about is the locomotion, or the movement of the rover. So most of the rovers that you've seen on Mars already, like Opportunity and Spirit and Curiosity, are all wheel-based rovers. So this isn't the only way that we can explore Mars, but it is one of the best, especially with what we're doing right now. So ExoMars, just like those other two rovers that I mentioned, is a wheel-based rover. So if you have a look here, we've got a back axle here, which tilts, and then we also have this front axle that tilts. So this is called a rocker bogie system. And the idea is that we're on Mars and there's no person there to make sure that the rover's in a safe environment. So the rover has to be able to navigate some bumps, some rocks, and slips on its own. And that system kind of helps it do that. But it's not the only way we could explore. You could have legs, you could have a walking rover. I'm sure you might have seen some of the really incredible stuff that Boston Dynamics are doing with rovers that can walk, jump, do backflips. So that could be a potential way that we go in the future. You could use sleds. You could do an airborne rover like the new Ingenuity that's going alongside NASA 2020. There are tons and tons of ideas. If you wanted to go to, well, if you were going to a planet with liquid on the surface, you would have to, again, entirely change that design. But for Mars, so far, wheels are kind of our main way forward. So the next thing that we have to talk about is our power source. So everything on the rover, everything to make the rover drive, to make the rover see, and to send us information needs a power source. So the ExoMars rover is powered by solar panels. So if I show you just the top, that's what these kind of shiny black tiles are on the top. So the solar panels on board ExoMars are really, really huge because we need a lot of energy to be able to power this sort of thing. But the other way that we could power a rover like this is using a radioisotope thermonuclear battery like Curiosity does. So if you've ever seen the Curiosity rover, at the back of the rover has a really large kind of cylindrical shape. That's its thermonuclear battery. So what happens? It uses an entirely different type of energy that's kind of intrinsic to the rover. So it doesn't rely on sun exposure, and it doesn't rely on being able to get enough power from the sun. So it gives it a little bit more freedom with where it would be able to land on the surface. When we're choosing a landing site for ExoMars, we have to make sure there's enough solar power to power the rover and make sure we can get all of our science done. So there's a little bit, again, of a trade-off between the technology you want to use and then what and where you can go on the surface of Mars. So the next thing that you have to think about when you're building a rover are things like navigation cameras, location cameras, and hazard cameras. So like I said before, there's no one on Mars to mind the rover. So it has to be able to look at the surface itself, feed all that information back to us, and get a really good 3D understanding of the surface. I've just knocked the solar panel off. So it does that in a number of different ways. So some of our main sensors we have up here got our navigation cameras, we have our location cameras, and then around the rover, we have hazard cameras. And all that information, all of those images are fed back into a program that gives the rover an understanding of the surface around it so it can try and avoid falls, pits, large rocks, and things like that to stop us getting damaged. And the last thing we're going to talk about is our payload. So this is the most exciting bit because this is how we do our science. And these are the instruments that Anya and I work on. So I'll actually maybe just take the top of the rover off just now so you can see, but this is the head of the rover. So it stands at the top of our 2-meter mast, and this is an instrument called PanCam. So PanCam is one of my favorites, maybe my favorite. It's a stereo imaging system. So that means just like us, it uses 2 different sensors to see, just like our 2 eyes. But instead of just seeing in red, green, and blue the way our eyes do, PanCam can look in 12 different wavelengths in each eye for lots of different reasons. So it's going to look at color, so we get some nice images back, and it's going to look at different wavelengths, so different colors of light that can tell us a little bit about the surface of Mars and what minerals are present. So once we understand the mineralogy of the rover surroundings, we can start to see what processes might have happened if there was water, if that location could maybe have preserved signs of life. Just below the PanCam instrument, we have ISM. So this little gray one here, which is again like a spectrometer. So it's looking at the fingerprints of different materials that we're interested in. But instead of just looking at 12 wavelengths in the visible kind of near infrared that we can see, it looks much farther than that. So it looks far into the infrared, and it looks at lots and lots and lots of different channels. So the trick is though, PanCam can see the entire scene in front of it. ISM can only see one little spot. So again, this is kind of the undergoing theme. There's a little bit of a trade-off between the best possible results that we can get and how they actually work on the surface of Mars. So that is all of our little ExoMars rover, including PanCam. Oh, actually, hold on, I've missed the drill. So that's terrible because the drill's amazing. So one of the really cool things, this is part of our payload, one of the really cool things about ExoMars is it has this 2-meter drill on the front. So this is it here, can rotate. It also actually has a camera instrument just on this side called Oppy. So again, we can see some really nice detailed images. But once we use PanCam and ISM, HRC and Oppy to understand the surface, what we're looking for is signs of life on Mars. And the surface of Mars is highly irradiated. It's really, really destructive. So we're going to be looking underground, and that drill is going to be able to get us far enough below the surface that we can get past that really harsh radiation barrier. So we're going to get some really amazing subsurface samples and hopefully find some signs of life in them.
Okay, amazing. Let's now pass it over to Katie, who's going to show you how you can make your own out of whatever you've got at home in your recycling, in your craft box, and you can have a go and do it along with us.
Fantastic. Thanks so much, guys. Before we do get started though, we've heard a little bit about Rosalind Franklin, but we don't really know that much about other rovers. What else could we put on our rover? So Nina's going to take us through a few different rovers and landers that have been up to Mars so we can have a think about what kind of experiments that we want our rover to do.
Thank you so much, Katie. I'm just going to share my screen because I have a selection of my favourite spacecraft that have landed on Mars, and I wanted to share them very quickly with you this morning. So, very quickly, these are essentially lots of different shapes, lots of different sizes of robots, landers, rovers, and I think I kind of wanted to start at the beginning with my very favourite one, which is, share, there we go, is Mars 3. So Mars 3 landed on Mars back in 1971. It was the very first spacecraft to make a soft landing on Mars. I'm not going to say it was a successful landing because the spacecraft survived for about 20 seconds after getting to the surface of Mars, didn't get to do much science. But you can see this is the spacecraft here, this object. You can see it's got solar panels, so much like the Rosalind Franklin rover, this is actually a combination of the orbiter, which dropped the lander off, and the lander as well. The equipment on the lander included things like television cameras, pressure sensors, thermometers, all essentially to find out what the surface of Mars was like. But the reason I really like Mars 3 was because it should, if it had lasted for more than 20 seconds, it should have deployed the very first rover on Mars. Unfortunately, it wasn't able to do that, but this is a picture of the rover that should have gone for a wee explore. And the reason I like this one is because, unlike the rovers that came later, this one didn't have wheels. This one actually had skis. So we didn't really know what the surface of Mars was going to be like. So these skis made sure that it wasn't going to sink into the Martian dust. And if the lander had actually lasted a little bit longer, it would have been able to explore the surface. We'll move on to a slightly more successful mission now. This is the Viking 1 lander. So this was an American mission that landed in 1975. To give you an idea of the scale of this spacecraft, it was really big. This is a scale model of it next to the astronomer Carl Sagan. This is a model of it in the desert in America. Gives you an idea of what it would have looked like on the surface of Mars though. And Viking 1 lasted for 6 years on the surface of Mars. It was an amazing piece of kit. It had 4 experiments on board, which were designed to look for signs of life on Mars. Now, 3 of those experiments returned a negative result, but one of them actually sent back a positive. And since the 1970s, scientists have been arguing over whether this positive was a false positive, it was a mistake, an error in the equipment, or if it was actually proof that there was life on Mars. We are hoping that either the Perseverance rover or Rosalind Franklin or both are going to maybe definitively answer that question, and hopefully that argument that's been raging for quite a long time will cease at that point. The reason I quite like Viking 1, not just because of those amazing experiments on board, was because it actually took the very first picture of the surface of Mars from the surface of Mars. So most of these spacecraft had cameras on board, so this is maybe something to consider when you're building your spacecraft, your rover, your lander, your helicopter even. And this is actually the very first picture of the surface of Mars that Viking 1 took. So I know that this sort of black and white, slightly grainy picture with sort of rocks and dust, and you can see the rover's footbed over in the bottom right corner. I know it might not look like much to you, but this was the very first time we got to see what the surface of Mars looked like up close. It was a pretty exciting photo to be able to see back in the 70s. We're going to move on to a rover that I actually remember. I remember this landing. It was a pretty exciting time. This is the Sojourner rover. And this was part of the Pathfinder mission. So you'll see quite a lot of these spacecraft are kind of two-parters. So things like the Mars 3 that had a rover, orbiter and lander. Sojourner had the Pathfinder lander and the Sojourner rover. This rover was only about the size of a microwave. So again, we've got lots of different sizes of spacecraft. And it was I do apologise, I have a cat in the house who's having a moment. This was the very first spacecraft to actually rove on another planet. And to give you an idea of how far it managed to go, it covered a distance of about 100 meters over its 85-day mission. And I know that might not sound amazing, but given that it was only supposed to last a week, that's pretty impressive. It lasted well over 10 times that. So it did quite well. You can see it's starting to look more like the kind of rovers that you might recognise though. It's got the solar panels on top. It's got those chunky wheels which help it move around the surface of Mars. When it comes to longevity of missions though, I think it's quite hard to beat these two. So these are the twin rovers, Spirit and Opportunity, which landed on Mars back in 2004. These were launched about a month apart. Again, you can see that there's solar panels here, those lovely chunky wheels. And this is actually a picture of Spirit. Could be a picture of Opportunity though. They were pretty much identical. And these spacecraft had an initial planned sort of mission length of about 90 Martian days, which is 92 and a half Earth days, because a Mars day is slightly longer than an Earth day. They ended up actually lasting quite a bit longer. So Spirit, the one that you can see here, survived for 9 years. It spent the kind of tail end of its mission stuck in a sand dune, so it was doing a lot of stationary science. Opportunity though, remarkable piece of kit. It survived for 14 years on the Martian surface, only going quiet back in 2018. We're all quite sad to lose it because both of these spacecraft did some amazing science. They were essentially kind of Martian geologists. What they were doing was looking not for signs of life, but for signs of water, which Anya said is what we're looking for when we look for conditions that are favourable to life. We look for water, we follow the water. And they found all sorts of evidence for there having been a lot of water on the surface of Mars in the past. So again, they're sort of working out where it might be good to send spacecraft in the future to look for life. The next, in fact, this is one of my favourite pictures. I nearly forgot about this one. This is actually a real picture of Opportunity. We know this is Opportunity because it took this photo of itself on the surface of Mars. So again, they're both equipped with cameras so they can explore the surface and send back images to Earth for us to work out where they're going next. So maybe the first Martian selfie. I think that's quite impressive. Now, the next one, Sarah actually touched on earlier. This isn't on Mars yet. It is en route to Mars though right now. This spacecraft is the Ingenuity helicopter, and it's attached to the Perseverance rover on the way to Mars. It was launched earlier this year. And this spacecraft is actually going to be the very first helicopter to fly on another planet. It's a pretty remarkable bit of kit for that reason, but I also think it's quite impressive because it's going to help us figure out how we can send these kinds of spacecraft, not just to other planets, but to moons in our solar system. So we're hoping to send a spacecraft called Dragonfly to Saturn's moon Titan the next few years. And again, that's going to be a helicopter. That's going to be something that can hover above the surface and explore even more than our rovers can. So you can see that these spacecraft come in all sorts of different shapes and sizes, have all sorts of different bits of kit. And I hope that's some inspiration for you to make your own Mars rover. And I'm going to hand over to Katie, who's going to show you how you can do that.
Wow, that was really exciting. There's so many different rovers that have been up to Mars. And now we're going to get a chance to make our very own. So before we do, we want to have a think about all of the rovers that we've seen. And we're going to think about what we want to put on our very own, because we're not making any of the ones that Nina showed us. We're not making Rosalind like Sarah showed us. We are making our very own. So have a think. Do you want it to look for water? Do you want it to look for life? Or do you want it to look for something completely different? We're going to need a few things to start before we make our rover. We're going to need some clean recycling that we can get inside our house. So I have an egg carton here, which I'm going to use for the body of my rover. I've also got some extra card to add a bit of colour if I want it, and also to make some of the science experiments to go on board. I've got some like sticks or skewers and some straws as well, just to add a bit of structure and some height to the rover as well. I've got myself some cardboard wheels because I want my rover to roll around on the surface of Mars. And to put it all together, I'm going to need some sellotape and also some glue as well. So before you start making it, it's probably a good idea to decorate it before you get started. So grab some pens, some pencils, some felt tips, anything you want to decorate your rover. And the first thing I'm going to do actually is I'm going to put my wheels on the rover. So I've got my skewers here, and I'm actually going to put the skewers through my egg cutter. So it comes up the other side. There we go. And I'm going to put my wheels on each side like this. So we've got something to roll around on the surface of Mars. I've got some sellotape that I've already cut, and I'm going to use those to help stick my wheels on, because the last thing we want is our wheels falling off when our rover gets up to Mars, because there's nobody up there, like Sarah said, to fix it. So we need to make sure that it's nice and sturdy. I'm obviously going to put some wheels on the back as well, because 2 is not going to be enough. You saw on Rosalind Franklin that there was 6. And that's because the surface of Mars can be really uneven. It might be a bit sandy in some places, or it might have big rocks in other places. So you want to make sure, however you choose for your rover to move around, that it's going to be able to kind of navigate around and on top of those rocks and that kind of uneven surface on Mars. So wheels are a great idea. Maybe several wheels to get over those. Maybe the sledges or the skis could be quite good as well. Or even if you're really wanting to kind of go crazy, you could make a helicopter, which is just super exciting. So there we go, those are my wheels. And the next thing I'm going to do is I'm going to think about the science that I want my rover to do. Now, I'm really excited about what's underneath the surface of Mars. We've seen some really exciting photos about what it looks like on top. We even have done quite a few experiments about what we can see and kind of test for on the surface of Mars. But what is underneath? So what I want to do is I want to make a drill. And for my drill, I'm going to use one of my straws, and I'm going to fold it so I can attach it to the front of my rover. And to make a nice shiny drill, I'm going to use some tin foil. So just a small piece of tin foil. I'm going to add that to the end of my straw, and I'm going to make a nice long drill so I can go deep into the surface of Mars. Now, I know that sometimes the tinfoil comes off when I put it onto my straw, so I'm going to use some sellotape as well to stick that on. There we go, but I have a nice drill there, and I'm going to use the bendy part to put that onto the front of my rover. Now, the other thing that I think is really important is how we're going to see on the surface of Mars. Because we want to take some cool selfies, we want to see more of the surface, and we want to make sure that as far as we can, avoid bumping into anything or falling off a cliff or getting stuck. So we need to make a camera. I'm going to use some of my cardboard here, and I'm going to make a box for my camera, and I'm going to put it on one of my straws. And that straw is going to be the mast that holds the camera above my rover. So if we stick it all together with that sellotape, you can see that I have a nice cardboard camera for the top of my rover just there. And I've put it on the straw so I can have a nice tall mast to go on top of my rover. So now I think the last thing to think about is how we're going to power our rover. A lot of the rovers that we've already sent up have solar panels on the top because they can generate their own power using the heat and energy from the sun. But that does restrict us about where we can go on the surface of Mars. So maybe if you want to go everywhere, you would use a battery. Or if you know you want to stay maybe towards the center or somewhere it's going to be really sunny, you can use solar panels. What I've done is I have actually folded some of my card and I've covered it in tin foil that you can see just there to make solar panels for the top of my rover. And if we look at it all together now, this is my rover. And what I need to do now is I need to think of a name. I'm not really sure. I'm going to have a think about that. But I know for sure that Nina has named her rover and she's put some pretty interesting stuff on it as well.
Yep, so I went down a similar route to you, Katie. I had to think about what I was interested in on the surface of Mars. So I've also attached a drill to mine. We've got a camera as well. But one of the great Martian mysteries that I'm quite interested in is the Martian atmosphere. So I put a little atmospheric sampler there because methane, a gas called methane, has been found on Mars in kind of really unusual concentrations. Sometimes it appears in quite high concentrations, sometimes it's barely there at all. We're not sure where it's coming from, whether it's evidence of life, evidence of interesting geological processes, even of volcanoes still ticking away under the surface. We're not quite sure, so that's what I would send to Mars.
Fantastic. And I think Sarah might have made a rover as well to go along with her Lego rover. Sarah, what do you have on your rover and did you give it a name?
So mine's a bit of a cop-out because it's basically the ExoMars rover because I love it so much. But if you have a look here, so we have our rocker bogey wheels, we have some solar panels, we have our PanCam eyes so we can see lots of different things on the surface. So one of the things I'm most interested in is understanding the spectra on the surface of Mars so we can kind of understand what we're looking at. And PanCam and ISM and things like that are really key to it. So this is my little, and a little drill just to make sure we can find those little like water bears or whatever we have hiding underneath the surface.
Fantastic. And now one of the things that we did talk about was solar panels and how that can limit where we put the rovers on Mars. So when they are building rovers, how do they decide where to put them?
So this is another super complicated part of sending a rover to Mars. So the first thing that we think about when we're selecting a landing site is what science we want to do. So ExoMars is looking for signs of life. So like we said earlier, you follow the water, you look for minerals, so different materials on Earth that form in the presence of water. So if I just grab the globe, I can show you where ExoMars will be landing. So let's have a look here. So Oxyoplanum, that's our ExoMars landing site, is around here. So if you notice, that's pretty close to the Martian equator. So if we're sending a solar powered mission, we have to make sure that there's enough solar power to run all of our instruments, which is why ExoMars had to have a landing site that was near the equator and with plenty of sunlight. But before we can kind of look at our engineering constraints, what we want to do is look at the surface of Mars and see where might have evidence of life. So Mars has different epochs in time, just like the Earth. So like we have the Jurassic, the Cretaceous, and things like that. So we have three main ones on Mars. We have the Noachian, which is the oldest. So that's over about 3.7 billion years old, that surface of Mars. Then we have the Hyperion, which is a little bit younger, and that's up to about 2.9 billion years ago. And then we have the Amazonian, which stretches right up until till now from 2.9 billion years ago. So we think the most habitable time in Mars's history was right back at the start in the Noachian. We think there was liquid water. We've seen geomorphological evidence. So that's things like ancient riverbeds, ancient deltas that look like there was standing water and flowing water at different points on Mars. So what we're doing, first thing they thought about when they were selecting landing sites is where that science can be done. So we look for these older surfaces. It's really cool how we age the surfaces on different planets. We look at cratering and things like that, but that's a whole other day and a whole other talk. So we look for these older surfaces, and then we use our orbiters that are around the planet to look for mineralogy that we're interested in. So we use orbiters, so satellites going around Mars, to look at the shapes of the landforms, so those deltas that I mentioned, or we look at the spectra, so the fingerprints of different minerals, and we look for things that might have life. So once we've done that, that's great. That's step one. That kind of cuts down our surface of Mars to the things that we're interested in. But after we do that, then we have to think about how we're going to land our rover. So the Curiosity rover and NASA 2020 will use a sky crane, so a kind of booster system. The way the ExoMars rover will land is a parachute system. So if you're using a parachute, you have to make sure that your elevation of your landing site is low enough that there's enough time for your parachute to be slowed down by the very thin atmosphere on Mars. So it takes a lot longer to slow down something as big as a rover on Mars than it does on Earth because the atmosphere is so much thinner. So again, that kind of cuts out all of our high points and leaves us, most of the northern hemisphere is a little bit better for kind of low elevation landings. And the last thing is our power mechanism, like we talked about. So ExoMars needs solar power, so we have to put it near the equator, somewhere with lots of sun. But the other thing to think about is somewhere that we don't have a lot of dust. So you might have heard about Opportunity before, but like Nina said, 14 years, incredible mission, found some of the first signs of water on Mars, really amazing. It was caught in a dust storm on Mars, and it's one of the issues it had was getting enough power to be able to keep going. So that's on top of being able to get enough power in the first place, we have to try and make sure that we don't get our solar panels too covered in dust or the power is a bit limited. So it's quite complex. And we decided, or they decided, I wasn't actually involved with landing sites, that the best place for the ExoMars rover to land would be really near Krishnagnisha here on the surface. Oh, actually, a good thing to mention here. So this is a little bit of a whirlwind tour of how you find your landing sites on Mars. If you guys get in touch and want to borrow one of the roving Roslin kits, or even just use the resources that we have online already, you'll get to work through all of this and then design your own landing site. So these are good sites for rovers, but we also have in the hopefully near future, because this is my dream, is that we're going to send people to the surface of Mars. And the things we need to send people are a little bit different. We need some access to frozen water or water. It's pretty limited. We have to use frozen water on Mars. So we might want to look further towards the poles and things like that. So lots of really exciting things for upcoming Mars missions with where we might land. So if you borrow a Roving with Rosalind kit, you can learn all about it and then design your own.
Fantastic. Thank you all very much. If you'd like to put all your videos and unmute your microphones as well, then we can see everyone, because we've got a zillion questions. Well, 46 questions. I mean, it's, maths is not my strong point. So let's get through this fairly quickly. We've answered some already. You can see those on the Q&A. We've answered some as we've gone along. I've answered a couple, and the other members of the team have answered a few. But let's go through. And I think you probably answered some of these, but it'd be nice to just reiterate them. And it's a question from, we don't know who this is from, but there were a few along these lines about power. And I think, Sarah, you mentioned this. But the question is, how has Curiosity stayed alive for many years without running out of power? And maybe you could just go through the different sort of power options you've got if you're on Mars.
Yeah. So like we've said 100 times, we have solar panels on ExoMars, but Curiosity has a radioisotope thermonuclear generator. So it's using a nuclear power source. So we do use nuclear power sources here on Earth with nuclear power stations. They're really, really high energy power batteries, basically. So the lifetime of those is really, really long. It's much longer than the normal batteries that we're used to in our phones and things like that. So Curiosity has a really extended lifetime because it's using an RTG. With solar panels, they degrade over time, as most electronics do, but it's a pretty long lifetime as well. It's more limited by the battery that it's using, which is usually lithium ion or something like that, which is quite similar to what we have in our phones, which I'm sure, as everybody knows, like they plummet after like a few years. So they're kind of limited by what stores their power, not by what's generating the power. But Curiosity has a lot of life left.
I was going to say, they've also got to survive, haven't they, the Martian night?
Yes. So it's the temperature ranges on Mars are crazy high. So it's like 200 degrees of a difference. So all of the electronics that we have on board these rovers have to be thermally insulated well enough that it can survive the Martian nights, which are pretty treacherous. Okay,
so let's go through some of the other questions here. Here's an interesting one. How do people control the rovers? And that's from Bo, age 11. I don't know who wants to answer that question.
I can kind of give you some insight. So the way it works is at least at the very start of missions, you have kind of rotational teams. There's always somebody monitoring the rover's progress. So you've got an engineering team that's doing the navigation, the pointing, and then you have a science team that's doing all the analysis of the data that's coming back. The really cool thing about this is you actually have to practice before missions happen for this sort of thing. So basically what they do is they send a kind of play rover out into like the Atacama Desert or somewhere that's quite Mars-like, and then they lock all the scientists and the engineers in a room together and make them play as if it's a real mission. It's pretty crazy timeline. So I think somebody asked about kind of Wi-Fi and connecting on space, in space. So we do have a kind of like space internet called the Deep Space Network. So that's one way that rovers can communicate back with Earth. But the way ExoMars and most rovers do is they communicate with an orbiter that's going around Mars. So the Deep Space Network, the rover has to be facing where on Earth it's trying to transmit. You get a little bit more of an extended window if you have an orbiter, but it's still very short. So you have maybe 2 hours to analyze all your data, see where you want to go next, plan your route, send it back to the rover on Mars. And if you missed your window, you've missed a whole day of operations. So it's pretty time intensive task.
And also, of course, you've got the time delay between Earth and Mars, which changes. I mean, I think it can be up to 24 minutes each way. So you've got a signal coming from Mars that takes 24 minutes, and you've got to send the signal back that takes 24 minutes. So it's not like they're kind of driving in real time.
Yeah, there's no real time kind of connection. What a lot of the rovers do have on board, so I talked about all those cameras that they have, the navigation, location, hazard cameras. All of that feeds into like a 3D model of the surface. So some rovers have automation where they can pseudo autonomously drive around the surface, avoid hazards and things like that. And they get input if there's anything that the rover kind of gets stuck with. So any like big drop or large rock, it'd be like, okay, I don't know what to do. Give me a hand from the engineers.
Okay, so we've got a question now from Year 5 at Jarvis Brook Primary School. And I guess they're talking about the real rover here. So the question was, how long did it take to design and build the rover, as opposed to the ones you made out of cardboard?
So this is a really, really varied answer. So ExoMars has been in development for decades. It's been a very, very long time. So it depends on the technology that you want to use and how long it takes to kind of get that from first concept all the way through to being built. But decades isn't unreasonable. But as we go forward and we understand the technology we're using better and we develop better ways of using it, it gets a little bit shorter. But I think one of the Mars rovers was 6 years. I think the UAE Mars rover was 6 years. I might be wrong. So as we get on in time, our understanding gets better, our techniques get better. But decades isn't unreasonable.
Just add to that as well. It's really interesting with NASA because the Curiosity rover that's going strong, that landed in 2012, they pretty much did the same again for their new rover, which is on the way now. So Perseverance, or the Mars 2020 rover that NASA built, is on the way to Mars. That'll be landing in a couple of, I think 3 or 4 months' time. And it near enough is sort of a copy paste of Curiosity with updated instruments. NASA basically thought, well, we've done really well with Curiosity. We know it works. We've spent a stack of money designing this, and we've shown that it can do some amazing science. And I can't tell you how cool some of the stuff it's done, even day in, day out now, 8 years later. So with the Perseverance rover, it kind of does look kind of the same. So it's really interesting that we have some totally new, amazing things like Ingenuity, the helicopter, never been done before. It's sort of a test drive with Ingenuity. But then we've also got Perseverance as well, which is a tried and tested method. And that's a really important thing about space, is we've kind of got to push the boundaries whilst also doing things that we know work, because getting to Mars is really hard. So we've got to, make sure things aren't going to break when they get there.
Yeah, we want to minimize risk as much as possible.
It's funny, that leads on actually rather nicely to a question from Suzanne. How do the rovers get to Mars? So who would like to talk about rockets?
So either Anya or I could do this, because I think we've probably spent a lot of time studying the rocket equation in our astrophysics degrees. So the way anything gets anywhere else out of the solar system has to be launched on a really large rocket. So it uses a lot of fuel and it has to get to a speed where it can escape the velocity of the escape velocity of the Earth. So it depends on how much money you have to spend on a mission, but generally what we do is we look for transfer windows that minimize the amount of fuel that we need for the rockets or the spacecraft to get to another planet. So for things like Huygens, it does kind of slingshots around other planets to get in the right direction, rather than use fuel to do like kind of small course changes. So what the ExoMars, what the Curiosity, what 2020 have all used is our closest approach with Mars and Earth. So once every 2 years, we get this nice little window where it only takes 9 months for us to get to Mars. And it kind of, essentially, we spiral out from Earth's orbit around the sun, and we intercept Mars. We come around Mars once or twice, and then they kind of come into descent.
Okay, thank you very much. That's great.
Richard, I have a couple here, if that's all right. I've got so this one's been in like really early, this one, so I think we do need to ask it. So English Fairy Tales was asking, why is Mars red? So I've got to get that in somehow. And CM Constantine asking, question. How much of an atmosphere does Mars have if a helicopter can fly there? That one might fall to Nina, because you did bring up the helicopter, I believe.
I did. So the Martian atmosphere is very, very thin. We think the reason for that is because a long time ago, Mars lost its magnetic field. So its molten core solidified, lost its magnetic field, and the solar wind sort of blew that atmosphere away, or any atmosphere it might have had away. So Mars has got this incredibly thin atmosphere. They essentially designed Ingenuity, and I did have to look this up because this was a question that I was interested in. They actually designed Ingenuity by putting it into a vacuum chamber. So the same sort of thing that they use to test other spacecraft. They reduced the pressure right down to the same pressure as it is on Mars, so much, much lower than it is on Earth, and tested it in there and made sure it could actually fly in that really thin atmosphere. Is that?
Oh, cool. And the Mars is red thing, who wants to come in on that? So I still haven't convinced myself I know.
So the surface of Mars is red because it has a really high percentage content of iron oxide. So essentially the same way we get rust on Earth, like a kind of fine dust that's covering the entirety of the surface of Mars. It's quite brown, like when you look at it as like a fine powder on its own, but it gives Mars its beautiful kind of ethereal red hue.
Okay, so I have a question. I think everyone should have a shot at this one. It's from Thomas, but it's also from Cameron and Grace. How long do you think it will be before humans will get to Mars for the first time? I think we can all have a go at this. And you have to hold us to this, of course. You have to come back and say, no, you got that wrong in a few years' time. Sarah, do you want to go first?
Yeah, I'm stuck between being really optimistic because I really want to go to Mars, and being really realistic. I think I'm going to be very vague. In several decades, not saying how many, but several decades, we're already testing some of the stuff we need. So on board Curiosity, there's an instrument called MOXIE, which is harnessing oxygen from the Martian atmosphere, and it's essentially, I think it's a 1% model, so it could be scaled up 100 times and be big enough for a small group of people to function on Mars. There's some big challenges, but we're not that far with the technology. For like the kind of living on Mars, getting to Mars is a bit more tricky. But I'd like to say 1 or 2 decades. Probably not, but that's what I would like.
Who'd like to go? Nina, would you like to have a go?
Yeah, I'm probably going to be equally vague. I'm not quite. Yeah, I think realistic rather than optimistic. I think in my estimations, I think sort of 2 to 3 decades. I think the biggest challenge is going to be getting people back from the surface of Mars. We have, there's getting to Mars. Space is hard. I think that's the kind of the thing, the place where we should start. Space is hard. We've sent, I think, almost 50, maybe over 50 missions to Mars now, and half of them haven't gotten there. So when we start sending humans to Mars, we really need to make sure that we have that technology absolutely nailed, because it's not like going to the moon, which is a 4-day trip. You're going to Mars, you're talking a spacecraft that needs to survive for 6 to 9 months on the way there. It needs to survive 2 years on the surface, being irradiated, as Sarah was saying, and then it needs to be able to launch and make that 6 to 9 month mission back. So yeah, I'm going to say realistically, I think 20 to 30 years. I do hope I'm still around to see it, because it's something we've been talking about in Planetarium for quite some time, and we're really excited to see it happen.
Katie, what do you reckon?
Oh, it's such a hard question, isn't it? Because everybody's really excited about the possibility of us like exploring another planet. I think ever since we set foot on the moon, we've set our sights on going even further. I would love to see it within our lifetime. So again, like maybe a couple of decades. But like Nina says, it's not necessarily the getting there, but it's the getting back that's going to be the hardest thing.
I would go and stay, in fairness. But
so Anya, have you got a guess?
I have a funny view about this that might be a bit controversial, but personally, I don't want people to go there until we've kind of done a lot of rovers. We don't know yet if there is life on Mars, and if we send humans there, we might kind of contaminate that life. So I want to wait until we've done a load more science robotically and, importantly, really cleanly in the areas with the highest kind of likelihood of life. We call it planetary protection, this idea that not only do we want to protect life on our own planet, but we want to protect life on other planetary bodies as well. So I think it'll be a while. I mean, a massive step that's going to come next is what we call Mars sample return, and that's actually bringing something back from Mars, because everything we've sent there is there and it's stuck. And what we're really working towards now is the idea that, okay, let's bring soil samples back. That's my baby, if you like. I analyze little bits of Mars in the lab, but the bits I analyze are meteorites. But it's always been about 10 years away, this idea of Mars sample return. For the last 20 years, it's been 10 years until we get a sample back. So going by that, the fact that it's been 10 years away for 20 years to get Mars sample return, I think it's going to be a while until humans get there because everything takes longer than we expect.
Alistair, you look like you are in space at the moment, so partway there.
Yeah. Oh, well, it's kind of good to ask. I think I want to see humans out there, and I think I agree that we are making a mess of the place. I'm also a bit scared that even our bits of rovers that we're leaving around aren't necessarily completely clean either. So there's so many things to think about. Maybe 10 years to the moon, 20 to Mars, something like that. What about yourself, Richard? Are you keen?
Well, yeah, I don't know. I mean, you think about Mars. It's a horrible place. Who'd want to live there? There's no atmosphere. It's dusty red. It's desolate. It's a desert. I mean, we're all struggling with lockdown. Imagine being stuck in a base there.
I'm sensing we
could be on Mars.
I have no desire. I mean, I'm a huge fan of exploration and sending people, but I'm inclined to agree that, I think we should sort out Earth first. But there's a lot of stages to go, and I think we're learning those lessons. We're now going back to the moon. We've got Gateway, so the space station around the moon, and the idea is to land a woman on the moon by 2024. That will probably slip a little bit, but we're sort of starting to do these things and go back to these things. But yeah, absolutely, as everyone said, getting to Mars is really, really hard. And do you really want to go? We're on this beautiful oasis, traveling through space, perfectly suited for us. Why do you want to go to Mars?
I'm sensing we've opened a can of worms here. I'm aware of the time, so I'm gonna combine a couple more questions here because this sort of follows on with humans aren't going to get there anytime soon. So Shetland Linkup has asked exactly how many cameras are actually on the Rosalind Franklin rover. At least I think that's what they're asking about there. I'm going to combine that because Karinder's asked a couple of questions. How does the internet work on Mars? And can we potentially get one of those cameras to live stream on YouTube so we can watch if we're not getting to be there? I think that's a deep question. Who wants to take that?
So the number of cameras, I can't tell you exactly how many hazard cameras there are because I'm not sure, but there are 2 cameras in PanCam's eyes, and then there's one you can see in our logo. That's the high resolution camera. And then there are 2 location cameras and 2 navigation cameras. So there's at least 7 there, plus all the hazard cameras. Live streaming is a little bit difficult because some of these instruments aren't built for live stream. So PanCam takes kind of single exposures through each one of its filters and things like that. And then there's the delay between picking up our data and then the rover stopping to send it back to the orbiter and the orbiter getting it to us. So live streaming is maybe a bit more difficult. Can't remember what the last part of the question was.
Yeah, I think it was just to do with if we were able to get the images. If we can't get them live, where could we get them from? And maybe that's because I think Curiosity might have a website, and then maybe Rosalind will be doing the same.
Yes, I think the current plan, the current discussion is to have kind of like the data released every day so people can see these images back from Mars kind of hopefully as quickly as we can. The actual kind of scientific analysis and stuff takes much longer, so you'll probably have to wait a little bit to see some of those results, but the hope is that you'll get kind of free access to everything as quickly as we possibly can get out to you.
Cool. And I'm afraid we're pretty much out of time, so I'm sorry, did you want to say something before I
was just going to say, just to add to that, there are like amazing resources on like the NASA website, for instance, on Twitter as well. You can follow some of the like rovers that are up there, and yeah, just have a wee look around because there is already an amazing amount of information that we've got out there.
Cool. And Anya, I noticed you'd put a link to the Rosalind, the roving Rosalind thing, so we can add that to the YouTube meta as well. So hopefully we can keep that link up for people. So yeah, that's it. I'm really sorry we're out of time. It's been amazing. The questions have been coming thick and fast. So let me just thank our experts again. So Anya, Sarah, Nina, and Katie, it's been amazing. Thank you so much. For those of you who are still hooked on Mars, this evening we're actually doing the 6 p.m. till 8 p.m. where again we're going to try and observe Mars live. If you haven't already tuned in for one of these sessions, we've managed to have it working. We've got enough people with enough telescopes that we might be able to let you see Mars through a telescope tonight. We're also still talking rovers this evening, and it will be an even deeper dive than what we're doing this morning. And then tomorrow we're talking Mars Careers Days. So there's another session at 11 in the morning and another one in the evening as well. So if you are champing at the bit to jump in and start doing some of this stuff for yourself, once you've built your models, then we will maybe see you on those sessions as well. So I think that's it. I'm just going to wave goodbye. We'll do our Brady Bunch goodbye. Thank you so much.
Thank you, everyone. Thank you.
We will see you all again.
Thanks, everyone. Bye.
Bye.